Hello, and welcome back to my series of lectures on global climate change, based on my recent book with Ivo Welsh, Global Climate Change, The Pragmatic Guide to Moving the Needle. And today we're going to talk about a basic subject that not everyone understands, even though it's the fundamental source of global warming, which is how do greenhouse gases work? And we need to start where we ended in part last time with the makeup of the atmosphere. Here it is again. And it's easy to exaggerate the greenhouse gases shown in green because they're such a small fraction of the overall atmosphere. Let's put aside water vapor for a second because that's often not included in the makeup because of its unique characteristics, but we're going to talk about that a good deal today. But the three major greenhouse gases, particularly carbon dioxide, methane, and nitrous oxides, in total are less than 1/2 of 1/10 of 1%. They're talked about often in parts per million. For example, with carbon dioxide, 0.0410% would be 410 parts per million. And in recent times, or I'm coming up to November of 2020, that's probably chinked up to 0.420 or 420 parts per million. So you don't want to exaggerate the notion that the atmosphere is full of greenhouse gases. What it has is important and will cause global warming. But still, we need to keep things in balance. So how does global warming work? Well, the starting point, of course, is solar radiation. The sun bathes the earth in electromagnetic radiation. How much? Well, on a summer's day at noon, the sun will be pushing into the earth energy equivalent to about 1,000 watts per square meter. But it's not always summer. It's not always daylight. What we really need to do the proper calculation for global warming is how much energy does the sun put in per square meter of the Earth's surface on average over the full year, day and night, winter and summer. And the answer to that is 240 watts per square meter. So if we think in terms of a basic schematic, here's the sun. It's putting in 240 watts per square meter. Ignore for a moment the effect of the greenhouse gases. Then in equilibrium, the energy coming in, the yellow line, has to be balanced by the energy going out, the red line. So if the sun is putting in an average of 240 watts per square meter, the Earth must be re-radiating that back to space, or it would be getting warmer if the sun was putting in more than it was radiating out, or it would be cooling if the sun was putting in less than it was radiating out. And it takes a while for this to reach equilibrium, maybe a century or so, but in terms of geological time, that's nothing. So most all time, the Earth is going to be in equilibrium. And from that, we can compute what the average temperature of the Earth ought to be. And I've done that in a simple spreadsheet here. So let me tell you how this works. At the top is the average solar radiation, which I've said is approximately 240 watts per square meter. There is a well-known law from physics called the Stefan-Boltzmann law that says that the radiative input has to equal in equilibrium the radiative output, which is given by E, the emission coefficient, sigma a physical constant, and T to the fourth power. Notice that the output of radiation is very sensitive to T, and that's good news for us because not that big a T is necessary in order to restore equilibrium. We'll explain that in a minute. You can solve that equation for T, since you know the 240 watt input. And the answer always comes out in terms of Kelvin. As an aside on measuring temperature, we tend to use centigrade and Fahrenheit, but those are based on the freezing and boiling point of water, which is arbitrary. It'll be different on every planet. It's even different in different parts of this planet. Kelvin is based on the physical concept of absolute zero. So 255.1 Kelvin, as shown there, is 255.1 degrees, and the degrees are equivalent to centigrade, above absolute zero. So when you solve the Stefan-Boltzmann equation, you get the temperature in terms of Kelvin, 255.1, which is minus 18.1 centigrade, or minus 0.5 Fahrenheit. In other words, if the world was a perfect absorber and reemitter of radiation, that's often called a black body, the average temperature would be well below freezing, and the Earth would be a giant snowball. It's unlikely that multicellular life would have ever arisen in such an environment. But that's not the Earth. The Earth today has an average temperature of 287.2 Kelvin, which is 14 centigrade, or 57.2 Fahrenheit. In most, all of that is due to the greenhouse gases. So, greenhouse gases are obviously a very good thing for life on this planet, but there can be too much of any good thing, and Venus is a perfect example. If I do the same calculations for Venus, the average input is 464 watts per square meter because it's quite a bit closer to the sun. That implies an average temperature of 301 Kelvin, or 28 degrees centigrade, and 82 degrees Fahrenheit. Certainly warm if that's the average temperature globally year-round, but not impossibly hot. Unfortunately, the makeup of Venus's atmosphere is about 95% greenhouse gases, and therefore the actual average temperature is 870 degrees Fahrenheit, hot enough to melt lead. So, the role of greenhouse gases is clearly very important in determining the average global temperature, and therefore we want to see what this implies with respect to the greenhouse gases that humanity has been emitting into the atmosphere. So let's go back to the schematic and talk exactly about how greenhouse gases work. As shown, the radiation comes in from the sun, warms the Earth re-radiates back outward. But the atoms in the atmosphere can be thought of as little vibrators. They're constantly jiggling. But if the frequency of the radiation doesn't match the rates at which they're jiggling, the radiation just passes right through the atmosphere and out into space. However, if there is a matching, then the jiggling atoms absorb the radiation, they jiggle even more, they get excited, and then they re-radiate. And they re-radiate as shown in this schematic in all directions. But the radiation coming out was all going out. Now it hits the atoms in the atmosphere and it goes in all directions, not just out. Some of it comes back as added radiation. So the total radiation received by the Earth is not 240 anymore. It's 240 plus the amount that has been re-radiated back toward the Earth by the greenhouse gases. That's the greenhouse effect. And it only applies to certain gases. That's why they are referred to as greenhouse gases. Going back to the atmosphere, the two key ones, nitrogen and oxygen, do not have this property. The way they're jiggling is not related to the radiation coming out of the Earth at the frequency determined by the Earth's temperature. So it just goes off into space. But the greenhouse gases have this property of absorbing and re-radiating, some of which comes back to Earth. And that is the reason that we have a greenhouse gas effect. And that is the reason for, if I look at this famous chart now called the hockey stick chart, why we see this dramatic increase in dramatic in terms of the scale of this graph, in terms of CO2 and temperature. Let me explain exactly what this graph is, because you see it all the time in the press and everywhere else. CO2, which is shown as the dotted red line, is marked on the right-hand axis. And you can see that for most of the time, beginning in about 400 BC and going up through the Industrial Revolution, the greenhouse the CO2 level was about 280 parts per million. And then with the beginning of the Industrial Revolution, it launches upward to where it is today, which is 420 parts. Now that's about a 50% increase in CO2 concentration. Physicists can tell you, based on the Stefan-Boltzmann law and taking into account other complexities, how much the global temperature should rise for a 50% increase or a doubling, let's say a doubling in the CO2 concentration. And the answer is that a doubling leads to about a 1 centigrade rise in the Earth's temperature. That's what's required to have the radiation outgoing equal to the radiation ingoing after you've had an increase in CO2, which is pumping some of the radiation back. Now, in fact, that 1 centigrade rise for doubling, we haven't doubled yet. We've only gone up 50%. So the theory predicts about a half a degree rise centigrade in global temperatures. But they've been more than double that, double the predicted rate. Why? What's going on? And this is one of the critical facts that is often overlooked in the popular press. So let's go back to the atmosphere for a minute. We haven't talked about water vapor, which actually is a key player. Notice that water vapor is about 10 times more abundant in the atmosphere than CO2 is. And water vapor is also a greenhouse gas. In fact, water vapor accounts for about 65 to 85, depending on the model that's used, of the total greenhouse gas effect. So the biggest player is not carbon dioxide or the other more minor GHGs of methane and nitrous oxide. It's water vapor. And water vapor has not been influenced by human activity. So how can we say that human activity is causing this spike? And the answer provided by climate scientists is that there's a feedback effect. As you increase CO2, temperatures rise. As temperatures rise, the atmosphere can hold more water vapor, or will hold more water vapor. as more water vapor is held, temperatures rise further, and you get a feedback or a multiplier effect. And it's that multiplier effect that explains why, whereas the pure CO2 effect would say that temperatures would have risen by less than half a degree, in fact, they've risen by, as this chart shows, if we look here, here's the pre-industrial level of 0, and we're now up over 1 degree centigrade. That reflects the magnifying impact of water vapor. So, when the IPCC or other professional groups attempt to forecast temperature rises associated with increasing CO2 concentrations, they are taking account of the water vapor amplification effect. So, to summarize, greenhouse gases are a good thing. Without them, the world would be a frozen snowball. However, we can have too much of a good thing. And as greenhouse gases rise, the Earth's temperature must rise to maintain a radiation equilibrium. In that context, CO2 plays a central role because it's been increasing due to human industrial activity. But it is not CO2 alone that leads to the warming we've observed. It is CO2 plus the water amplification effect. So that's what we'll be dealing with in future lectures. We'll assume that global temperatures are determined by a combination of rising CO2 and then the amplification effect of water vapor. Look forward to seeing you in further episodes. Thanks.